minus v I t, and I will multiply, divide by square root of t, and I will take xj of t minus j, and again, and that's dij. So that's the asymptotic variance. Right, so that's the result, and I think that the at least strategy, there are technical difficulties, of course, but the strategy is quite simple, and it is based on one very fundamental trick. So the trick is the following. Very useful. So the tool. I mean, there are two tools. One is the most fundamental tool, and actually it came from the paper with Albert van Jank, Tomasz Komorowski, and myself from SPA, and also from the paper with Tomasz Komorowski and myself from Journal of Statistical Physics. So the situation is the following. Assume that the velocity satisfies such equation, SPD. And I will have RDW. And assume that A, F are translation invariant. So they are operators, but with constant coefficients. But could be pseudo-differential, but necessarily translation homogeneous. It could be on the whole space or on the toric. That doesn't matter. So a translation invariant. And I assume also that this process is stationary in space. So I will assume that R dw stationary in space. And okay, I'm interested in this equation. Okay. Not plus. So that's of course the integral formulation of my passive scalar. Xs ds. So assume that X is a solution adapted to the filtration given by the Wiener process. So I assume this and define such process eta Tx as u of t x plus x of t. Right, so we shift u in direction of x. Why we do it? Because if we, okay, you have here u as xs, so we have eta as 0. So x will be the additive functional of eta. So that's something. So eta as 0, ds, right? That's by definition. It's obvious. So we have this, and actually we have, I mean, always we have this, but not always eta is a Markov process. So we would like to have that x is an additive function of a Markov process. So if we if we shift U solution to any PDE, that's not always, we will not get a Markov process. So it turns out that eta under this condition, eta satisfies this equation. So that's the same. That's the same. There's no chance. But there is a contribution, and that's eta t0 calculated zero gradient of eta of t. So it's extra term here. It's very natural. Plus r dw. And the point is that this process, in fact, depends in some way on x. So we will take two different, say, initial values. We will have two different x's, but in fact, we will have two processes. One will be x0. The second will be, say, x1. So there are two different initial values. So this will be cylindrical Wiener process. This will be cylindrical Wiener process. But this together is not a Gaussian process. So this is the marginals are Wiener processes, but not the two. They together. It's not. So anyway, that this will be some process. And as soon as we are interested in the law of x, we can forget about this difference, because the law of the solution does not depend on the particular choice of the Wiener process. So we can forget about this, but we have to have in mind that we are allowed only to talk about the law, not about the, say, different particle. Okay, so we have this. So let us apply this result to this. It works. So we will get, so this is a strange notation. I will have B naught, so I will have B psi t. So it will be the B naught plus this term. So at this moment, I will introduce omega t on x is psi tx plus x t, right? And I will write equation for omega. So of course the omega is, Laplace operator omega minus b omega dt plus, and okay, I don't want to change to introduce the notation. I will keep the same noise, but we have to, it's a bit abuse of notation. So summing up, we can assume that we are interested in such situation that omega satisfies this equation. B is B naught minus omega 0, okay, gradient omega. That's the new nonlinear term. So we have this, and x of t is this. As calculated at 0 ds. Right. So at this moment, I reduce everything to the study such situation. I have omega solves such equation. x is given by this formula. And actually, in the formulation of the theorem, I cheated a bit because I didn't say anything about in which sense x is a solution. The problem is, of course, that u is not continuous in x, right? It's continuous in time and L square in right. So the regularity for strong solution, I think, is continuity in H. I will write W1, 2, but this is because not to be confused with V, which was introduced here, and L2, and that's the, say, W22. But it's more or less a disk, right? This in dimension 2 is embedded in C, but not this one. So there is a delicate problem how to define the solution. But okay, might talk the solution is x, is this. It's given by the formula. And the integral converges because the omega, this is a continuous function, this is a L2, a square integrable function in the space of continuous functions. So there are no problems with the convergence of the integral. Right. So now let's try to prove the law of large numbers. How to do with this? Okay, I would. So, law of large numbers. So, what we would like to prove? We would like to prove something that 1 over t integral 0 to t psi omega s ds converges to some constant, where psi of omega is k omega of 0. Right? That's yeah. I just rewrite this in this form. It's nothing. What we can suspect that we have something about the uniqueness of invariant measure. That's probably we can prove. We can prove. So we can prove to have this. We need that there is a unique invariant measure. So mu invariant measure for omega, and we need some stability. So I need something like this. Some mu naught t converges to mu. Right? Weakly. So that's the something which is in our range to prove. Yes, we have to start with this. But actually, I will. Yes. Okay, so let's assume that we have this, and how this will work with this. So I think that with this we will get this. Right? So it's not what we would like to prove. We would like to prove the that this converges in probability. We have only the convergence. There is a one delicate problem that usually we have this convergence. I mean, this is a weak, so we have to apply this for psi regular, continuous, and bounded. And of course, psi here is not continuous and not bounded, right? Because it's yes, that's operation is not continuous. So that's the big problem. But nevertheless, assume that we have something like this and try to use again in more refined way this. So what is enough to prove? It is enough to prove this, and it's enough to prove that this. And that's right? Where psi bar is the psi minus this average. That's obvious because we will get not convergence in probability, but in that too. So psi is psi minus psi mu. All right. So at least since we have here this as a 2, we need to rewrite this using the semigroup, right? But this is not difficult. Oh. So maybe I will. So I would like to just to continue this. So the first line is obvious. So the right-hand side. Right-hand side is the same as the expectation over t square integral. I would put 2 integral 0 to t integral 0 to small t psi omega s psi omega t ds dt. Right? That's obvious. It always works. Now I can use the Markov property. So I should take the conditional expectation of this with respect to omega up to time s. So I will get what? T square t. Okay, expectation psi of omega s pt minus s psi of omega s ds and dt. Right, that's obvious. Okay, so we see that we can rewrite everything in terms of the semigroup, because now I will write that this is ps of psi pt minus s psi, and I should take the omega 0, and probably I should integrate with respect to omega 0. Okay, so this is something which, and actually it works for law of large numbers. So for law of large numbers, it's enough to prove this. So I can continue later, but this is enough. The problem is, of course, for the central limit and for the asymptotic variance. For the asymptotic variance and central limit, we need a spectral gap. So for asymptotic variance and the limit theorem, we need a spectral gap. Spectral gap. So what it means So I would like to, at this moment, I will be not quite precise. So I need that pt psi minus psi invariant measure in some norm, which is should be I have some freedom to choose, is E2 minus gamma t times maybe another norm of psi. So that's what I need. So we borrow this from the paper by Martin Heirer and Mattingly. That's from 6. And also, we need some regularization property of the semigroup. And this is from paper by Mattingly and Pardue. So Mattingly, Pardue. I think it's the same here. So I will cheat from this moment. So I will assume that I have this for all psi, and I will not be concerned about the norm. This is the delicate problem because in our case we would like to apply this to a non-continuous psi. Because technically that's something which one has to do. Of course, the papers by Heirer and Mattingly Pardue were concerned with stochastic Navier Stokes, but not this one, but with B naught. But the change is really, I mean, it doesn't change a lot in the proof if we replace B naught by this. So it's we check point by point and was absolutely the same result. So the same method works. So it's not a problem. Okay, so how much time I have? 10 minutes? 10 minutes, great. So maybe I will try to prove that I should sometimes when I'm talking on the blackboard I have tendency to forget about some other works. So it's a good, I think that Shirikian it is PTRF and 6 he proved central limit theorem for additive functionals for the stochastic Navier Stokes equation. And basically is the same method. So I think that, I mean, the difference are for which functional. Because of course it's the difference for which equation, but that's not a problem. The problem is rather on for which functionals, for which observable. Okay, so the key point, and this is the more or less consequence of this, is the existence of the so-called corrector. So what is corrector? Is this. Ah. So that's this. So if we have, okay, we need some rate of convergence to have the integrability of this. Of course, psi bar is psi minus this. So it looks good, but as I said, this formula is not 100% correct. So it's the main problem was to prove that this integral converges for our observable psi. So if you have this, then central limit theorem is quite standard. So how to prove that central limit theorem? So that's a short argument. The idea is to reduce central limit theorem of additive functional to central limit theorem to martingale. So I assume that we have central limit theorem for martingales. And I assume that we have this. So how to get martingale? So the idea is the following. So I would like to prove this over 2 psi omega s ds converges weakly to some n 0d. So that's my objections. That's my goal. So I can write that the left-hand side is 1 over, this is square root of t mt plus rt, where mt is what? Is chi omega t minus chi omega 0. And I would like to have that this is a martingale. So I should subtract what? I should subtract this, the generator of chi. Right? So there's a hope that this is a martingale if I subtract the generator. It's like an eta formula. Okay, but a chi is probably minus psi. Okay, so I will get that this is omega t, omega 0, plus integral 0 to t psi omega s ds. Right, so that's my mt, it's a martingale. So we can calculate what is r, or is the difference. So what's r? Rt is 1 over square root of t chi omega t minus chi omega 0. Okay, so we see that there is a hope, since we have square root of t in the denominator, that this will goes to 0. And we have a martingale, so that we can hope that we can apply central limit theorem for the martingale. And actually, there are plenty of different versions of central limit theorems for martingale. So we use a proper one. Maybe I will stop this, because I can continue also this, but if you use the fact that this integral is finite, then it's quite simple to prove that the limit is 0. That's very simple. And also it's quite simple to prove that the asymptotic variance exists, and you will obtain the matrix, that's your question, it will be something like the invariant measure of our system calculated on psi chi. I think it is the formula. But I don't think that this is very useful. So I mean, you have a formula. I think that I can stop.
Thank you. Question?
You say that V star is non-zero?
Yes, can I say? Yesterday I was sure that it is zero, but it's not zero. It's not zero.
V star.
V star is not zero. So the no, sorry, I don't know. That's I don't know. I knew that the D is non-zero, so that this metric is not trivial. But V star, I don't know. I haven't checked.
Isn't V star zero by symmetry?
I'm not it's not really symmetric. You have one point selected. So it's not that you have the solution is stationary.
But the Q,
So it's not
was it isotropic, I mean, or not?
Q. I mean that this Q is
The original one in the psi equation.
it's the same as here. It is isotropic. I mean it's diagonal. I'm not sure that.
Does it mean it's isotropic?
Because V star different from zero could be related to the inverse cascade, to the existence of bigger structures. And the ballistic behavior cannot happen if everything is just turbulent at small scale and there should be just a diffusion. Here the ballistic behavior is because there are...
Now the formula for V star is this, right? V star is the Stokes V is right? And now the question is can I use the symmetry? I have to check, but I'm not sure.
Other questions or comments?
The problem, sorry, is that omega is not, I mean, if I start from a stationary, the omega is not stationary in space. Because it's not an equation with a constant, I mean, with I selected the zero in some way. So it's,
If there is no flow, I mean, what is the situation if you have if you are looking at these deterministic flows like Albert von Jung does? Sometimes, I mean, there is a characterization, right? When there is for the deterministic cellular flow, when there is actually
deterministic with force or without force. Without force, I will have a convergence to zero.
No, I mean, if you are given the flow U, right? And if you are just looking at the so for the moment you are not looking at this this white noise in time, but you are just looking at these flows. I mean, then the question is usually whether the flow is in effect cellular or not, and because and it depends also a little bit on the. It depends on the regularity, right? If the regularity is too low of the flow, then still you have kind of the possibility of a drift, even if it's cellular. I mean, I don't know. Can one, for this stochastic equation, think about? I mean, whether this is cellular or not?
I mean,
Because you see, I mean, you can just do the symmetry where on the one hand you map U to minus U, and then on the other hand you swap, you flip space around. right? And then you change the sign of the Wiener process. And the whole thing is completely symmetric under that transformation, and it would make the particle go in the opposite direction if V star would be non-zero. So it has to be 0.
Okay, so we thank the speaker again.